So this brings us to lecture 14, which is on topology. And topology in the limited sense, I mean, might be more accurately, we'd say topology of, the real numbers. And I mean, more specifically, we might say metric topology of the real numbers. So it's the topology which is judged by the absolute value function, actually, and our traditional Euclidean notion of distance on the real line. But here's the fundamental thing. So the open ball is actually an open interval. You go, here's a picture. You got the center at A, right? And you're going plus or minus A plus delta down to A minus delta. That's a quote-unquote open ball. Now, in 2 dimensions that actually becomes an open disk. In 3 dimensions it actually becomes an open ball, but it's actually an open interval here in your usual language. And a subset of the reals is said to be open if for each point A and A there exists a delta such that the ball of radius delta is a subset of A. So any open interval is open because, so basically the point is, if you look at an open interval from, let's say, C to D, and then I'll draw another one here just to illustrate the 2 cases, right? Then, well, if A is, here, then basically you can do like this as an open ball that's inside the set C to D, and if your A is over here, you can use this delta. So here, delta equal to D minus A. Over here, delta equal to A minus C, right? So he says let delta be the minimum of A minus C and D minus A. Then the ball of radius delta centered at A is going to be a subset of A because you either got that or that. Okay, fine, yeah. And then in addition, his example 2.1, their example rather, I should say, this is from, of course, the textbook we've been using, which is, let me remind you the names of the authors. Beatrice Lafayette, Gerardo Lafayette, I think, well, I may be mispronouncing that, my apologies, and then Win Mao Nam, 3 authors out of, this is a PDF open textbook we're using. This is from 2018 edition at the moment. But anyway, let's see, let me get back to where I was. Okay, so continuing here. Here's a, he also mentions, of course, that the, they mention, of course, that the open interval from minus infinity to C and from C to infinity are both open, but the, if you include C, that's not open because you can't find, in fact, closed intervals are not open because if you look at like the closed interval, right, from C to D, think about that being your set, Think about that being the set, then, where was I? Oh, yes. And then if you look at, well, C is an element, right? Let's just focus on C here. C is an element of CD, right? So you could think about C playing the role of A in the definition 2.61, and yet there's no way any delta you pick, right? If you look at, C minus delta to C plus delta, that is not a subset of CD, right? So, and that's true for all delta, right? So therefore, there does not exist a delta greater than 0 such that B delta of C is a subset of C comma D, right? Therefore, the closed interval from C to D is not open. And that would still be true if we, didn't include the D, right? If you have an edge which is a boundary point which is included, an edge point which is included, you can make this kind of argument, right? And at the moment I'm using the term boundary point in an intuitive way. But anyway, so likewise you can prove that C to infinity is not open. So yeah. So theorem 2.61 here. The following hold: the empty set and the whole real line are open. The proof of that is very easy. The empty set is trivially open because there's no point to find an open interval around. To show that R is open, pick any point in R, right? Pick A. And then if you go, I don't know, how about A minus 1 to A plus 1? Well, that's a ball around A which is inside R. Therefore, R is open, since you can do that for an arbitrary point. The union of any collection of open subsets of R is open. All right. And then notice that this is an arbitrary union, right? The intersection of a finite number of open sets of R is open. So let's look at the proof of part B here first. Okay, so get that out of the way. Suppose we have an arbitrary collection of open subsets of R. That means that each of the family of the subsets is self-open, right? If we let G be the union of these open sets, let A be an element of G. What does that mean? That means that there exists an index, right, alpha naught, such that A is an element of G alpha naught. But then G alpha naught is open, right, which means that there exists a delta greater than 0, such that the ball of radius delta centered at A is a subset of G naught, because alpha G sub alpha naught, because again this is open, so there has to exist this open ball around A. But then what? Well, if it's a subset of G alpha naught, it's likewise a subset of the union, right? Because if you have a subset of one thing in the union, and of course G alpha naught is a subset itself of the union over alpha and I of G sub alpha, of course this implies that the ball of radius delta centered at A is also a subset of G. This union over all things is called G. So this shows then that an arbitrary point in the arbitrary union has an open ball around it, and inside the set again. And it follows then that by definition G, the arbitrary union, is in fact open. So what's different about intersection? What is it about intersection? Well, intersection is based on that notion that it's in all of the sets, that and, right? Whereas union is more based on or, right? And all right, so let's go through it. Suppose we have a finite collection, finite G1, G2, Gn, all open. We want to show that the intersection of this finite intersection is in fact also open. So take next point. We take a point, an arbitrary point in the intersection, A an element of G. What does that mean? Well, that means that A is an element of G sub I for each I, right? If it's in the intersection, it's in every single set. Now, moreover, since each set is open, that means that there exists, let's say, a delta sub I greater than 0, such that the ball of radius delta I centered at A is a subset of Gi. All right. So we've got n different balls to work with, and what we're going to do is basically find the smallest one of those, right? Find the smallest one of those. And so he just said let delta be the minimum of all the deltas. And that makes sense because this is finite, right? You can pick a minimum of a finite list. And so then, of course, delta is positive, and VA delta is a subset of G. Now, I think there's a little bit of daylight between this and that. I think it'd be good for there to be a lemma here. The lemma, I might add. The lemma I might add would be this. If delta 1 is less than delta 2, and I should say they're both positive, okay, then the ball of radius delta 1 centered at A is a subset of the ball of radius delta 2 centered at A. Right? And then maybe extend this inductively to n deltas, right? You know, the inductive extension of this lemma, which is really what we need, right? Delta 1 less than, well, I guess it's not the inductive extension. I don't know what to say about this. Well, anyway, delta, basically the point is, oh, let me erase this. That's what's going on here. Because the delta is the minimum of all the delta 1 through delta m, it follows that delta, the ball of radius delta is a subset of all of the balls. And as such, that means that the ball of radius delta is in the intersection of all the sets. And consequently, we get that the ball of radius delta is a subset of the G, which is the intersection of all the sets. So I think there's I mean, it's not a big deal what's missing here, but there's a little bit missing. All right. Nothing that's not pretty obvious, but, you know, goodness gracious, we do spend time to prove obvious things in topology quite a bit, so whatever. All right, so next up, the definition. A subset S of the reals is called closed if its complement is open. All right, so for example, if we look at the closed interval CD, right? I mean, if this is the closed interval from CD, it's going to be very embarrassing if this is in a closed set, right? Like that usage of the term closed interval, it better be compliant with this terminology, otherwise it's just a mess, you know. So what I'm going to do is I use minus for set difference, right? So the complement of R by the closed interval is what? It's minus infinity to C not included, unioned with D not included, sorry about that, unioned with D not included to infinity. But we have previously argued that, you know, what have we previously argued? Previously argued that this is open and that this is open, and we also know that the union of open sets is open, and so consequently the complement of the closed set is open. Therefore, the closed interval is in fact closed in this sense of the definition 2.6.2. Oh, okay, good to know. So here he's going to give you some examples like the closed interval, the closed rays to plus or minus infinity. These are all open because their complements are open sets, as we've discussed previously. And oh, this is also an important, this might slip past you, but a set containing just one point, right? So the complement, in other words, excuse me, if we take R and remove just the point B, that's called what he calls B complement, right? And that's exactly, like he says, minus infinity to B, union with B to infinity. And again, that's the union of open sets, which is open. So a singleton, a set containing just one point in the reals, is a closed set. So brings us to another theorem, theorem 2.6.2. And the theorem says that the empty set and the reals are closed. the intersection of any collection of closed subsets of R is closed, and the union of any finite number of closed sets of R is closed. So the tables have turned. Now we can allow arbitrary intersections of closed sets to be closed and finite unions of closed sets to be closed. And I would wager that the proof of this theorem is going to rest on De Morgan's laws. Most likely, right? Oh, look, the proofs of these are simple using De Morgan's law. Proof for B, for instance, take a arbitrary collection of open sets and form the intersection, right? Then the complement of that is the union of the complements. But since this is a closed, each of the sets is closed in the collection, the complement of the closed set is open. So we have an arbitrary union of open, which is open, which is to say that the complement of the intersection is itself open, which is to say that the set is closed. All right, there you go. Again, SC is open because it's the union of open sets, and therefore S is closed. Remember, S sub C is another notation for complement. So SC, the notation I've been using is S upper C is R minus S. It's take the real numbers and get rid of everything except for get rid of everything in S. All right. And in the proof of C is pretty much the same thing. It's just when we take a union of a finite number and we take the complement, we get the intersection of the finite number, and each one of those the intersection of the complements is an intersection of open sets. It's a finite intersection of open sets, which again, by the previous theorem, is open, and therefore the complement is open, and therefore the finite union is in fact closed. So the proof of part C is very analogous to the proof which is given for B. All right. Example 2.3. It follows from part C. Part C. From part C of the theorem and the example we just gave, that any finite set is closed, right? Because if you have a finite set, you can look at it as the union of, here's a finite set, right? A1, A2, AN, and that is equal to what? It's equal to the set containing just A1, union with a set just containing A2, union, union A, it's a set just containing AN, right? So any finite set is the union of a finite number of singleton sets, but we already know that each singleton set is closed, and since the finite union of closed sets is closed, it follows that any set just containing a finite number of points is in fact closed. So, cool. Theorem 2.6.3. A subset A of R is closed if and only if, for any sequence A sub n in A that converges to a point in R, it follows that A is also in the set. So in other words, a convergent sequence inside a closed set must converge to a point inside the set. All right, and here it is. So let's see here. Suppose A is a closed subset of the reals, and A sub n is a sequence in A that converges to little a. And he's going to go by contradiction. Okay, so suppose that the limit point's not in A. All right, since A is closed, that means that you can look at that means that its complement is open, right? And so since A is not in A, that means A is an element of the complement, right? And since the complement is open because A is closed, it means that there exists a ball of radius epsilon. Oh, now we're using epsilon. What happened to delta? Come on. Anyway, okay, fine, epsilon. Epsilon's the new delta. There exists a ball of, and has he always been using semicolons? What's that semicolon? I don't remember. Oh, yes, there has been a semicolon in all the balls. I think I just used a comma, or maybe I'm sorry, I seem to have modified his. I seem to have modified the author's notation for the open ball. I've been using b sub delta of a, whereas they've been using b of a semicolon delta. So just so you, all right, great. Anyway, there are various notations. All right. Anyway, sorry, I got distracted. So A is closed. There exists epsilon greater than 0 such that the ball of radius epsilon is a subset of the complement, right? But since an converges to A, that means that there exists a natural number n such that a sub a minus epsilon less than a sub n less than a plus epsilon. Right, because the sequence converges to A, right? So we can go sufficiently far out to get sufficiently close to the limiting value, because this is equivalent to absolute value of a sub n minus a being less than epsilon, right? That's equivalent to this inequality, right? And anyway, but this implies that a sub n is an element of the complement A. But remember, why is that a contradiction? That's a contradiction because the sequence is a sequence in A, right? So the range of this sequence is a subset of A, technically. What that means, right? A1, A2, and so on and so forth, forever and ever, any finite n is an element of A, right? And we just proved that it's not an element of A, and that's a clear contradiction. What that means then? That means that A must be an element of A. Now, let's see here. That would seem to me to be half of the theorem's proof, right? Because it's if and only if. And let's see what we got here. Now prove the converse. All right, very good, very good. Sometimes every so often I'll find a proof of a converse which is left off because it's too simple, but this one is apparently not. So let's prove the converse. Suppose by contradiction that A is not closed. All right. So the converse, we're assuming that for any sequence an and A that converges to a point A, that so we're assuming this property that any sequence that converges to a point that any sequence in the set A, its limit its limit point, the set, rather the point to which the sequence converges is also in A. So that's the assumption here in the converse direction. Now we're trying to show, given that assumption, this subset of A is not closed towards a contradiction, right? Because what we'd like to prove is the subset of A is closed. So suppose by contradiction that A is not closed, then the complement is not open, because if it was open, then it would be closed, right? If the complement was open, then the set would be closed. Since this is not open, that means there exists an A in the complement such that for any epsilon, there has to, if it's not open, there has to exist at least one point for which there does not exist a ball around the point, right? An epsilon ball. So there has to exist an A in the complement such that for any epsilon greater than 0, we have that the ball A of radius epsilon intersect with A is non-empty. Right? Because if it was empty, that would mean that that ball was in the complement, right? Okay. But if it's non-empty, in particular means that for such an A, for an A that's in this non-trivial intersection, and for each natural number n, there exists an A sub n such that the ball of radius 1 over n is intersect with A. So this holds for any epsilon greater than 0. So in particular, it holds for 1 over n. All right. And he's saying let A sub n be that point in that ball of radius 1 over n. Then that sequence, so defined, is in A, and it's also convergent to A because the absolute value of A sub n minus A is 1 over n by construction. But then this contradicts this is a contradiction since A is not an element of A. Right. Therefore, A is closed, because we've proved that if you assume it's not closed, we get a contradiction. So there you go. This is often a useful criteria, to show that a set is closed. This is the sequential test for closed. Take a convergent sequence in the set. If you can find it converges to a point outside the set, then guess what? That set is not closed. All right. So another related theorem. If we have a non-empty subset of the reals that is closed and bounded above, then the maximum of A exists. Similarly, if A is non-empty that's closed and bounded below, then the minimum of A exists. So the difference between, and I don't know if this has been discussed before, maybe it has been discussed in the section I skipped or something, I don't know. But the difference between maximum and supremum is that the maximum is an element of the set, and the minimum is an element of the set, if it exists. All right. For bounded subsets, the supremum and the infimum exist, I believe. But that doesn't have to be the case for a max and a min, right? Like, for example, the max of the open set 0 to 1, does not exist. You'd like for the maximum to be 1, but you can't use that because 1 is not an element of 0 to 1, right? Okay. So the theorem says basically, hey, if it's a closed set, the maximum's in there, if it's bounded. So let A be a non-empty closed set that's bounded above. Then, since it's bounded above, the supremum of A exists, right? Let M equals supremum of A. And, all right. So he says, to complete the proof, we'll show that M is an element of A. Assumed by contradiction, man, it's all contradiction in this lecture. Oh, well. Assumed by contradiction, M is not an element of A. Then M is in the complement, which, by the way, is an open set. So that means that there exists a open ball around M in the complement, right? M minus delta, M plus delta, subset of the complement. And that means that there is no A such that it fits in. Right, there's no A in here, right? I mean, A is not an, A isn't, there's no A with A an element of M minus delta, M plus delta, right? So that directly means that, there does not exist A with M minus delta less than A less than M plus delta. But the part of that which is interesting is the lower part. Now, how does he know A is less than or equal to M? What was M? M was the supremum of A, right? A is an element of A. So this is M is an upper bound for A, so that's where he's getting that from, right? But of course, this contradicts the fact that M is the least upper bound of A. Because if there was no A with this, then you could replace M with M minus delta and use that as the upper bound, right? I mean, anyway, go back to proposition 1.51. There has to exist a point in the set between the supremum and the supremum less a certain positive amount, right? And if it's not possible, then we're violating the terms and conditions of proposition 1.51, and consequently it's in contradiction, right? So therefore, M must be the least, well, the contradiction is coming from assuming that M is not an element of A. So if M being not an element of A produced trouble, it must be that M is an element of A. And if M is an element of A, that means that we can say M is the max of A. Because essentially what a maximum is it's a supremum which is in the set. All right. And the proof of the proof for the closed and bounded below would be very, very similar. Just, replacing a bound above with a bound below, and m plus delta rather than m minus delta. And it's not proposition 1.51, it's the corresponding proposition for the infimum. All right, so definition. Let's see here. Definition, this is a pretty important one. A subset A of the reals is called compact if for every sequence in A there exists a subsequence which converges to a point in A. And sometimes this definition would be called the sequential definition of compactness, because it basically says a compact subset of the reals is one for which for every sequence in that set there exists a convergent subsequence whose limiting value is inside the set again. Blah. And what's his footnote here? This definition of compactness is more commonly referred to as sequential compactness. That's right. So here's an example. Basically, he's going to argue that the closed interval from A to B is compact. So take a sequence. That means the sequence is between A and B. So the sequence is bounded. And by the Bolzano-Weierstrass theorem, you can obtain a convergent subsequence. And if that convergent sequence converges to S, then, well, by the squeeze theorem, it follows that since that's above and that's below, and maybe it wasn't the squeeze theorem, maybe it's the comparison theorem for us in here. Well, that limits to A, that limits to B, and this limits to S. It must be that S is between A and B, right? And consequently, S is an element of the closed interval as desired. So we conclude that the closed interval from A to B is a compact set. All right. In fact, we can say more. A subset A of the reals is compact if and only if it's closed and bounded. All right. So, proof. Suppose that A is a compact subset of the reals. So we need then to show that that implies it's closed, it's bounded and closed, right? So he'll start with bounded. So suppose by contradiction A is not bounded. Then for every n, there exists a sub n in A such that A sub n is the value of A sub n is larger than n, right? But since A is compact, there exists a subsequence A sub n sub k that converges to A and A. But then what? So that means that the of course, we still have this condition for n sub k, so absolute value of A sub n sub k is greater than n sub k. But remember, one of our fundamental lemmas about subsequences is that n sub k is greater than or equal to k. So, like that. But then what? Well, that shows that this values of the subsequence are unbounded, right? So the limit as k goes to infinity of the subsequence is, the absolute value of the subsequence is infinity. But that's a contradiction because the absolute value, because we're we've assumed that the subsequence converges to A, right? We can't also have that the subsequence diverges to infinity. That's a contradiction. All right. Therefore, A is bounded. Now we also need to show it's closed. To show it's closed, right, let A sub n be a sequence that in A that converges to a point A in the reals. By definition of compactness, A sub n has a subsequence, right, because we're assuming A is compact at this point in the proof. So A sub n has a subsequence A sub nk that converges to, let's say, B in A. Then, all right, so, okay, so that's the point. So we're taking a sequence that converges to a point A. We're looking at a subsequence of that sequence. Well, that has to converge to some point B in A, and by definition of compactness, it has to be a point in A, right? but remember our earlier theorem that a convergent sequence, converges to the same value as any subsequence. So since the subsequence converges to B, it must be that the sequence also converges to, well, A is equal to B is essentially the point. And since B is an element of A, it follows that A is an element of A, and therefore we've taken an arbitrary sequence in the set, and we've shown that it converges to a point in the set. And then it follows then that the set is closed. So we showed that compact implies closed and bounded by this argument here. Now, conversely, suppose that you have a set which is closed and bounded, and take a sequence in A. Since A is bounded, all right, that means that the sequence is bounded, right? Because if it's inside the set A and A is bounded, it means that a subset of a bounded set is bounded. The range of that sequence is bounded. So the sequence is bounded, and by the Bolzano-Weierstrass theorem, we know that there's a convergent subsequence, right? And what do we say about that? It has a convergent subsequence, which he calls A sub nk, and so the limit of A sub nk is A, give it a name, and so it follows now from theorem 2.63 that A is an element of A, and this shows that A is compact as is desired. Let me remind ourselves what theorem 2.63 was. 2.63 was a subset of A is closed and bounded if and only if for any sequence A in A that converges to a point in A is in A. Okay, so it's the sequential characterization of closed. That's what theorem 2.63 is. And what we've just shown is that oh man, sorry guys, lost my place. Oh, that's the wrong page. Come on. I need more memory. For the converse, suppose A is closed and bounded. Let AN be a sequence in A. Okay. Since A is bounded, the sequence is bounded, and by the Bolzano-Weierstrass theorem, it has a convergent subsequence. All right. And A sub nk, and then that, of course, that has to converge to A, right? But okay, that is itself a sequence in the set, and since the set is closed, it must converge to a point inside the set. But that is to show that the subsequence converges to a point inside the set, which means that A is sequentially compact. All right, fine. It's clear. Next definition. A cluster, a limit, or an accumulation point. A be a subset of the reals. A point A, not necessarily, but rather a point in the reals, not necessarily in A itself, is called a limit point of A. If for any delta greater than 0, the open ball the open ball centered at A with radius delta contains an infinite number of points of A. And furthermore, a point A in A, which is not an accumulation point of A, is called an isolated point of A. All right. And notice it has to be for any delta greater than 0. All right. So, for example, A equals to 0 as a limit point of A. Okay, great. Any open ball around 0 contains a bunch of points from 0 to 1, and from like 0 to a half or whatever. B equals to 1, well, that's not an element of A, and yet any open interval around 1 has, I think it's good to draw a picture here. So here's 0, here's 1, right? So any open ball you can think about drawing around 0, you're definitely going to have points inside the set, right? And likewise, any open interval you draw around 1, you have points inside the set over there, right? And so 0 and 1 are both limit points of A. he says, in fact, any point of the interval 0 to 1 is a limit point of A, right? In fact, the set 0 to 1 has no isolated points. Okay, fine, great. And the integer doesn't have any. The integers don't have any limit points. In fact, every element of the integers is an isolated point. That is true, because you take any, if you think about the number line and think about the integers on the number line 0, 1. I mean, the terminology makes a lot of sense, right? These are isolated points in the sense that you can find. Now, there exist open balls which contain other points in the integers, right? But isolated point, and a limit point is one for which every open ball contains an infinite number of points, right? So there are plenty of open balls around 0, for example, which just contain 0 in the integers, right? And likewise for any of these numbers, right? Like 2, you can take any ball of radius delta. If you pick z, an element of z, right? Then the ball of radius delta of z just intersected with the integers is just z again for delta less than 1, right? You have to have a radius larger than 1 to reach more than just the integer z, all right? So every integer is isolated. And this is, finally, not finally, a more delicate example here. A is the set 1 over n is a natural number. In this case, 0 is the only limit point of A, because if you take any open ball around 0, you've got infinitely many points of the form 1 over n. And he says all elements of A are isolated points, right? Yeah, because you pick any particular point in A, you can always, find a ball of radius delta small enough such that it just contains that point and doesn't contain infinitely many points, right? All right. Technically, you have to find a ball that doesn't contain infinitely many points, but I usually think about it in terms of finding a ball which just contains the point in question as a means of testing isolation. But technically, that's not the definition. He just said not an accumulation point, right? But, in all honesty, when I think isolated point, I think there exists a ball of radius delta such that the ball of radius delta around the point just contains that point. To me, that's what isolated point means, like intuitively, but whatever. I think those are probably logically equivalent. Now, example 2.66. G, an open subset of the reals, every point. For an open point, every point is a limit point, because every point contains a ball of radius delta around the point inside the set. And a ball of radius delta contains infinitely many points. All right. He says, in fact, more is true. If G is open and A is an element of G, then A is a limit point of G with A removed. Well, that's also true, because if you can, fine. So, yep. All right. And then here's a variation of the Bolzano-Weierstrass theorem. Any infinite bounded subset of the reals has at least one limit point. So, all right, let A be an infinite subset of the reals, and A sub n a sequence such that you have distinct values, so the sequence isn't repeating. All right. Then, let's see, your infinite bounded subset of R has at least one limit point. Sequence such that we we have distinct values, all right. See theorem 1.2.7. All right, I'm curious. What was theorem 1.2.7? Just a second here, folks. Come on. Where'd you go? Oh my. Theorem 1.2.7 is suppose A is an infinite set, then there exists a one-to-one function from the natural numbers into A. Whoa, okay, well this is a sneaky step then. Let A be an infinite set. Alright. And let A sub n be a sequence of A such that A sub m is not equal to A sub m for m not equal to n. In other words, he's assuming the sequence is injective. Alright, that is theorem 1.2.7. Alright, I gotcha. Suppose an is bounded by the Bolzano-Weierstrass theorem. There exists a convergent subsequence A sub nk. Let B be the limit of the subsequence. And if we pick delta greater than 0, then there exists k such that A sub such as the subsequence is in the ball of radius delta for k beyond big K. And but this set A sub nk such that k is greater than k is infinite. The reason it's infinite is because, remember, the sequence has distinct values. So we have a set that goes from big K on out of values in the sequence, which means that we have infinitely many different values. And more than that, well, what does that mean? Those values are inside the ball of radius delta centered at B, right? That means that B is a limit point because it has this ball of radius delta, which has infinitely many points in the set in it. So by definition of limit point, it's a limit point. Oh, there you go. Any infinite bounded subset of the reals has at least one limit point. Yeah, okay, cool. Another definition. So the following definitions concern what is often known as relative topology. So relative topology is the study of topology relative to some subspace. Topology. In fact, all of the results of this section foreshadow the more abstract study of topology. So topology is one of the more well-developed theoretical aspects of modern mathematics. And we've known for some time that these things we're talking about with respect to the real line can be generalized to essentially abstract, essentially arbitrary spaces. And like you can give a meaning for topology on very, very strange sets. And not just that, there's not just one notion of topology for the real line. There's actually many different notions. The one I'm describing in this lecture is called metric topology because it's based on the ordinary Euclidean distance, so-called Euclidean metric, which is just the usual distance function. But there are other things like the lower upper limit topology, and weirder things still. If you study something called algebraic geometry, there's something called the Zariski topology, which is just even weirder. Anyway, topology is a big topic in mathematics, and we're just kind of showing you, in this lecture, we're just really touching on the sort of most, well, I would say, benign version of it, all right? Anyway, so subset of the reals, then if we have if D is a subset of the reals, then V, a subset of D, is open. Basically, if there exists a delta such that the intersection of the ball of radius delta with D is a subset of V. So, theorem. So, let's see here, how can I say this? Well, theorem. Come on. Let D be a subset of the reals, then a subset V of D is open if and only if there exists an open subset G in the reals such that V is the intersection of D with G. All right. So suppose V is open in D, then by definition there exists a ball of radius delta A. Well, for every A rather in the V, there exists delta A such that the ball of radius delta centered at A intersect with D is a subset of V. And so you can just take the union for all of those things and call it G, but the union, notice this is an arbitrary union, possibly arbitrary. Anyway, it's a union. I mean, I guess V could be finite, whatever, but it's a union of open balls, right? So G is open, and great. So then what? Come on. So it's a union, which is of open things, which is open. Moreover, V is a subset of G intersect D, which is a subset of V. Therefore, V is equal to G intersect D. So the reason this is a subset of subset of V is what? Oh, because remember B, let's see here, B intersect D is a subset of V for all A. If it's true for all A, then that means the intersection is also a subset, or excuse me, the union rather, is also a subset of V. So, yeah. And of course, this is giving us double containment, therefore equality of the intersection with V. Conversely, if V is the intersection of G and D and G is an open set, then for any A and V, we have A is an element of G. A and V. Well, yes, A is an element of both G and D in that case, right? So if it's an element of G, and G is open, that means there exists a delta ball of radius, open ball centered about A of radius delta, which is a subset of G. But that follows then that the ball of radius delta centered at A is intersect with D is a subset of G intersect with D, right, because of that, which is equal to V by assumption. Which is to say that, we've proved that the subset of V is open in D, according to the definition, right? The definition was to show that the ball of radius delta, that there exists a ball of radius delta centered at A, which when intersected with D is a subset of V. That has to be able to be done for arbitrary point in V. But this holds for an arbitrary A and V, so we got it. All right. Now, so here's an example, and so for like the half open, the sometimes called Clopin interval, 0 to 1. So 0 included, 1 not included, and V is equal to 0 to 1/2. We can write. He says we can write V equal to D intersect with -1 to 1/2, right? And I mean, sure, -1 to 1/2 is open, sure, and so we've got the intersection of D with an open set is equal to V. It follows then that V is open in D. So the open sets with respect to D can be different than the open sets with respect to just the reals itself. So, yeah. In other words, the idea of what's open in the subspace or the relative topology is different, a little bit different than what's open in the overlying space. And the issue basically is with edges, All right. Anyway, there's more that you can say there, but I'll stop there. But so here's a theorem about relative topology. If D is a subset of the reals, then the following holds. The empty set and D are open in D. The union of any collection of open sets in D is open in D. The intersection of any finite number of open sets in D is open in D. So in fact, the reason for this theorem being here is that these three items are actually used as the definition for a topology abstractly. A topology on a space S is a collection of sets for which the empty set and the whole set are in there, and arbitrary unions of the sets inside the family are in there again, and finite intersections of the sets inside the family are in there again. The family of sets is called the topology for the space. And so the topology is generally like a sort of a subset of the power set of a space. And this theorem shows that, in fact, the relative topology, as defined in definition 2.6.5, actually squares with the abstract definition of topology, which I don't think has been given in your book, and that's okay. Maybe I'll say more about that later, but anyway, here's the definition of closed with respect to the subset. It's if the complement with respect to the subset is open with respect to the subset. No. And theorem, if D is a subset of the reals, K, a subset of D is closed in D if and only if there exists a closed subset F such that the intersection with D. So basically it says that your notion of, you can also characterize closed subsets of the set D as being intersected with closed subsets of the reals. All right. And so here's a proof which I'll skip here for now. And but there's the proof if you want to look at it. It's on page 59 of this text here. And let's try to wrap it up here in under an hour. Corollary 2.6.10, D is subset of R. The subset K of D is closed in D if and only if for every sequence X of K and K that converges to a point X bar in D, it follows that X bar is also in K. So that concerns, how sequences work and in this context. I think basically this is just saying that the sequential test of closed still works in the relative topology is what that basically says there. And then finally, theorem 2.6.11 says that, well, it's the analog. So this is the other thing is, you can either define topology in terms of open sets, which is what's dominantly done, or you could define it in terms of closed sets. And the definition of topology in terms of closed sets is that the empty set and the whole set are closed, that the arbitrary intersection of closed sets is closed, and that the finite union of closed sets is closed. And what this theorem does is it shows that the relative topology is a topology in the sense of as they're defined in terms of closed sets. But so there you go. I'm sorry I've kind of glossed over the proofs in the last page here. I'll let you spend more time, and of course you can ask me questions about them if you got them. But anyway, we will move on next time to the next topic, which I believe is in the next. In fact, this topic is kind of an outlier for Chapter 2. But of course, we're moving on to limits of functions, which is Chapter 3. That'll be Lecture 15. So, thanks, guys.